Okay, ready to dive in. We're tackling electricity today. It's everywhere, but we can't even see it. Crazy, right?
It's definitely one of those things you don't really think about until the power goes out.
For sure. So we got those excerpts you sent from, what's it called? Physics 2 Test 2 Waffles.pdf.
Sounds about right. Classic.
Yeah. And those circuit diagrams, too. You're not afraid to get technical, are you?
Gotta love a good circuit diagram. It's like a roadmap to how things work.
Exactly. So today, let's demystify some of these electrical concepts, like those aha moments, and then how it all connects to our tech.
Because who doesn't love seeing how things actually work, right?
Totally. Speaking of which, did you know you can actually store electricity? Like in a bottle or something?
Kind of. It's more like, imagine it like a tiny battery. That's what a capacitor is.
Huh. Okay, so it's like holding on to that electrical energy for later.
Exactly. And you can even make them even better at storing energy using these things called dielectric.
Dielectric. That sounds intense. Is that like a superconductor or something?
Not quite. Remember rubbing a balloon on your hair and then it sticking to the wall?
Yeah, classic static electricity prank.
That's the basic idea. The balloon gets negatively charged, and then it interacts with the charges on the wall. It creates these things called dipoles.
Okay, not gonna lie, I'm a little lost with the dipole.
So basically, the molecules in the wall, they kind of align themselves with the electric field from the balloon.
So if like the balloon's charge is influencing the wall, even without touching. Weird.
Exactly. And dielectric materials in a capacitor do something similar. By aligning charges, they actually let the capacitor store even more charge.
Wait, really? So more charge, more energy?
You got it. Plus, it helps them handle higher voltages safely.
Higher voltages, so it's like reinforcing a dam so it can hold back more water.
That's a great way to think about it.
Okay, cool. So switching gears a bit, when we flip a light switch,
Yeah.
do those electrons in the wires just like zoom around at the speed of light?
Funny you should ask. Nope. They're surprisingly slow.
Way serious?
Seriously. Think of it like those electrons are constantly bumping into stuff in the wire. Slows them down.
Huh. So what actually travels that fast then? If it's not the electrons, how does the light turn on instantly?
Good question. It's the electric field that's traveling super fast.
Oh, right, the field. Okay. So the electrons are taking their time, but that signal, that's what's moving at basically the speed of light.
You got it. Imagine it like a line of people passing a ball. The ball gets there fast, even if each person only moves a little bit.
That makes sense. And speaking of pathways, I've always wondered why some wires are super thick while others are like thin as a hair.
Oh, good eye. It's all about something called wire gauge. Smaller the gauge number, thicker the wire.
So there's a reason behind it. I always thought it was just random.
Nope. Thicker wire means less resistance, which lets more current flow through, like a bigger pipe for water.
Makes sense. So it's all about reducing that electrical friction.
Exactly. And speaking of resistance, you sent over some notes about superconductors. Those sound, well, super. What makes them so special? They're like the rock stars of conductivity. Almost zero resistance, especially at really low temperatures. We're talking 500 to 1500 amps, with almost no energy loss.
Whoa, that's insane. What could we even do with that kind of power?
So many things. Super efficient power grids, crazy fast computers, maybe even levitating trains.
Okay, now you're just messing with me. Levitating trains.
Hey, I said maybe. But for now, they're mostly used in specialized stuff like MRI machines. The cooling is still a bit of a challenge to make them mainstream.
Makes sense. Still, that's wild. Okay, let's jump to something a little less mind-bending.
Sounds good.
Our tech world runs on these things called semiconductors. They're in everything. LEDs, those amazing phone screens we have. What's the deal with those?
Semiconductors are like the middle ground. Not quite a conductor, not quite an insulator. They're special because we can kind of tweak how well they conduct electricity.
Tweak them.
Yeah.
How do you mean?
It's called doping. We add tiny amounts of other stuff to them to fine-tune how they behave electrically, like adding spices to a recipe.
Wow, so we can literally control how they conduct electricity just by, like, messing with their makeup.
Exactly. That's how we get them to do what we need, whether it's for a simple LED or something way more complex.
So cool. So about these photodiodes, I read that they're not naturally sensitive to color. How do our cameras take those amazing color photos then?
It's pretty clever, actually. You know how our eyes have cones that see color?
Yeah, like red, green, and blue cones, right?
Exactly. Cameras use filters like that. They put red, green, and blue filters over individual photodiodes to capture different wavelengths of light.
So each pixel is actually like multiple photodiodes with filters. That's so cool.
Yep.
Then the camera combines those signals to make the full color image. It's basically digital painting with light.
That's amazing. It's like we're tricking light into becoming an image.
In a way, yeah. It's all about using these components to manipulate light and create something incredible.
And speaking of incredible, we can't forget about the brains of it all, logic gates.
Ah, yes, those are essential. They're like tiny decision makers built using those semiconductors we were just talking about.
Right. And those logic gates are made with transistors, which are like tiny electronic switches, right?
You got it. And by combining them in different ways, we get different logic functions.
Yeah.
Embudo gates or
Yeah.
bar gates, those are the basics.
So it's like using light switches to make decisions. If
Yeah.
you have two switches controlling one light, an AND gate would be like needing to flip both switches on for the light to turn on. Exactly. And an OR gate needs at least one switch on for the light to come on. It's that simple, but when you scale it up,
That's how we get computers and smartphones and all that.
exactly. By combining tons of these simple logic gates, we can create incredibly complex digital circuits. It's mind-blowing when you think about it.
It really is. And to think, it all starts with controlling the flow of those tiny electrons.
And we've come a long way in figuring out how to do that.
We sure have. But you know what else is super cool? Piezoelectricity. Have you ever heard of crystals that can generate electricity when you squeeze them?
Wait, what? Really? I feel like I'm back in my high school physics class, except way more interesting. How does that even work?
I know, right?
Oh, yeah.
Apparently, it's all about the way these crystals are structured. When you apply pressure, it distorts their lattice, causing charges to separate, and boom, you get a voltage.
That's wild. So it's like they store energy and then release it as electricity when you squeeze them.
Pretty much. It's like having a tiny crystal-powered battery.
That's incredible. What do we even see that for?
All sorts of things. Ultrasound is a big one.
No way, really.
Yeah? You apply an electric field to a piezoelectric crystal, and it vibrates super fast, creating sound waves. That's how they see inside the human body without using radiation.
Wow, that's amazing. So they're like little sound wave generators.
Exactly. And it works both ways. Pressure can generate electricity, and electricity can generate vibrations.
Mind blown.
I know, right?
You know, it just goes to show that even the seemingly simplest things can hold such incredible potential when we understand how they work.
Absolutely. And that's what makes these deep dives so fascinating, wouldn't you say?
Couldn't agree more. There's always something new to discover and be amazed by.
It just goes to show you, you never know what you'll find lurking inside a crystal. But hey, while we're on the topic of circuits, one thing I've always found a bit confusing is the whole voltage drop thing.
Yeah, it sounds kind of intimidating, doesn't it? Like something bad is happening.
Exactly. But I guess it's just part of how circuits work, right?
Exactly. It's really just about the difference in electrical potential between 2 points.
Yeah.
Our source compares it to water flowing through a pipe.
Oh, I like those analogies.
Right.
Makes things easier to picture.
Right. So the voltage is like water pressure. And as the water flows, it encounters resistance. Those narrow parts of the pipe, the bends, that's your voltage drop.
So the voltage, like the water pressure, decreases as it moves through the circuit.
Exactly. And the more resistance something has, the bigger the voltage drop. It's like trying to push the same amount of water through a narrower pipe.
Gotcha. Makes sense. And batteries, those are like the pumps that create the voltage in the first place, right?
Exactly. They create that electrical pressure, that push that makes the current flow.
Okay, so that's why we talk about things like a 9-volt battery. That's the electrical potential difference between its positive and negative terminals.
Exactly. And that voltage difference is what drives the flow of electrons, the current, through our circuits.
Makes sense. So those Kirchhoff's rules I saw in the notes, those are like the rules of the road for how this all works.
Pretty much. They're two basic principles that help us understand how voltage and current behave in more complex circuits.
Okay, break it down for me. What's the first rule?
So the first one, Kirchhoff's current law, deals with junctions. Those are the spots in a circuit where, like, multiple wires meet. And it basically says that whatever current flows into a junction has to equal the current flowing OUT of it.
So it's like a traffic intersection for electrons. What goes in must come out.
Exactly. No electrons mysteriously appearing or disappearing, just following those paths.
Makes sense.
Mhm.
Okay, what's the second rule all about?
The second one, Kirchhoff's voltage law, is about loops in a circuit. It says that if you add up all the voltage drops around a closed loop, it'll always equal 0.
Wait, what? Add up to 0. How does that work?
Okay, imagine you're hiking, right? You climb up some hills, you go down some slopes, but eventually you end up back where you started.
Back at the same elevation, yeah.
Exactly. It's like that with voltage. It goes up, it goes down, but around a complete loop in a circuit, it always balances out to zero.
Okay, that's a really helpful way to think about it. It's
Yeah.
like those Kirchhoff's rules are the key to understanding how it all fits together.
You got it. And speaking of fitting things together, remember we were talking about photodiodes and how they're not naturally color sensitive?
Yeah.
So to capture color, cameras use those red, green, and blue filters we talked about. Each pixel on your camera sensor, it's actually a cluster of photodiodes, each with its own color filter.
Oh, that's right. It's like those old color TVs with the red, green, and blue dots. Each pixel is actually 3 pixels in one.
Exactly. And by measuring the light intensity for each color, the camera can then like reconstruct the full color image.
That's
Pretty
right.
cool, right?
It's seriously impressive, all thanks to these tiny components. Okay, another quick question about diodes, this time Zener diodes. Our notes mentioned voltage regulation. Those are important, right?
Totally. Think of a Zener diode, like a voltage bodyguard.
Okay, a bodyguard.
Yeah, like it protects sensitive circuits from getting too much voltage. They have a breakdown voltage. Below that, they block the current. But if the voltage goes above that point,
That happens. Does it like short circuit or something?
not quite. It suddenly lets current flow through in the opposite direction. It's like a pressure valve that opens when things get too high.
Oh, okay, I get it now. It's like redirecting the flow to keep things stable.
Exactly. We can actually fine-tune that breakdown voltage for different applications, making sure our electronics get a nice, steady supply.
So those Zener diodes are like the unsung heroes of stable electronics.
Yeah.
Protecting our gadgets behind the scenes. That's awesome.
Totally. They're in pretty much everything that uses electricity. And speaking of unsung heroes, those transistors we were talking about earlier, they completely revolutionized amplification.
Oh, right. They're what we use now instead of those clunky vacuum tubes.
You got it. Imagine trying to build modern electronics with those things. Bulky, inefficient, always generating tons of heat.
Not exactly pocket size.
Not even close. Transistors were a game changer. Smaller, more reliable, way less power hungry. They made everything possible.
It's incredible how such a small change could have such a huge impact. Didn't transistors also solve that problem of signals getting weaker over long distances?
Exactly. Remember how we talked about resistance in wires?
Yeah, that pesky thing.
Well, the farther a signal has to travel, the more it weakens because of that resistance. It was a big problem for things like, long distance phone calls in the early days.
Right. So how did they use transistors to fix that?
They figured out how to use them to amplify the signal. It's like putting little booster stations along a communication line, making sure the signal stays strong over those long distances.
So they're like signal relay runners,
Yeah,
passing it along and giving it a boost every so often.
exactly. And this wasn't just for phone calls either. Radio, television, eventually the internet. None of it would be possible without transistors.
It's amazing how much we take them for granted. Those tiny components make our connected world possible.
I know, right? And it doesn't stop there. Transistors are also how we build computers.
Wait, really? We were talking about logic gates before, but how do we get from those to like actually running programs and stuff?
It's all about combining those simple logic gates made with transistors on a massive scale. Just like letters form words and words form sentences, logic gates form more complex circuits.
So those logic gates are like the building blocks of computer logic.
Exactly. Millions, even billions of them working together to process information, make calculations, you name it. It's pretty mind-blowing.
It really is. All thanks to those tiny transistors flipping between on and off states like crazy.
And that's how our digital world runs.
It's crazy to think about how far we've come from those giant, power-hungry vacuum tubes to these tiny transistors that we could barely even see.
Right. It's a testament to human ingenuity, figuring out how to do so much with so little.
It makes you wonder, what's next? What kind of incredible things will we be able to do with electricity in the future? Any guesses?
Well, for me, the most exciting possibilities are in superconductors and bioelectronics. Imagine a world with lossless energy transmission, using superconductors to power our cities with incredible efficiency. Or think about bioelectronic devices that could interface with our nervous systems, treating diseases and maybe even enhancing human capabilities. It's like science fiction becoming reality.
Oh, now that would be a game changer. Sign me up for the bioelectronic future.
Me too. Though I wouldn't mind seeing wireless electricity become a reality either. No more tangled cords and searching for outlets.
Oh man, can you imagine everything just powered wirelessly? Now that would be truly electrifying.
It would revolutionize so many things. Definitely a future worth striving for.
For sure. Well, I think we've reached the end of our electrical odyssey. We've covered a lot of ground today, from those tiny electrons to complex circuits, and I hope you've gained a new appreciation for the invisible force that powers our world.
It's been a blast. It's amazing how much there is to learn about something we can't even see.
It really is. And to everyone listening, we hope you enjoyed this deep dive into the world of electricity. Until next time, keep those circuits buzzing.